how do we confirm that our correlation is statistically strong or statistically significant? Well, we can test it in terms of hypothesis testing. And that's not so hard so long as we follow the important steps in hypothesis testing, okay? We follow the steps, it will be fine because the steps will not change. So, step 1, state the null and the alternate hypothesis. What is the null? Well, look at this letter here. This is new. This letter here is the Greek letter rho. Okay, that's the Greek letter rho. It's not a P necessarily like an English P. It is Greek letter rho, okay, which corresponds to the R that we've been dealing with. So we can say that the rho, right, is similar to the R, which is the correlation coefficient. Okay, so we can get away with saying that. It's just that we're replacing the R with a Greek letter. All right. Now, the null hypothesis is that rho or R is equal to 0. And what does that mean? That means the correlation in the population is actually 0. Now, if we look at this relationship here, can we say there is a 0 in terms of copiers sold and sales calls? Can we say that the relationship is 0?
I would say no.
And why would you say no?
Because isn't it showing it's correlated, it's positive?
Exactly. That's exactly right. We would say, wait a minute, there's not a 0 relationship here. A 0 relationship looks like this, right? Where you have data points just scattered all around, no credible relationship that you could visualize. Even before you actually calculated an R, you would know that, or at least you would know that there's probably a 0 there because there's no relationship. But this one is very clearly a relationship. It's not perfectly linear because that's a straight line, but it's close. It's close. Whatever the R here is, it's going to be a high positive number. Okay? So if that's the case, then our null hypothesis being that R is actually 0, we hope is rejected, right? Because looking at the logic of the graph, it's clearly not 0. Okay, so we're going to test whether or not it is 0, right? We're going to go to another stage of scientific analysis by engaging in this hypothesis test. So H1, on the other hand, says that the rho is not equal to 0, right? Not equal right there and not 0 right there. So we're hoping that we do not reject H1 and that we reject HO, because that will be consistent with what we've constructed as a scatter plot. Okay, so let's test this at kind of our standard level of significance, where we have an alpha of 0.05. Okay, number 3, we're going to test hypothesis about a correlation using a t-stat. Right? What was the test that we used in the previous chapter? Was it T, Z, or something else?
Wasn't it F in the previous chapter?
It was F, right? It was F. We were looking at variances. We were looking at the testing of multiple means, whether or not they were equal to 0. Okay, so that was the F test. And before that, we were looking at Z's and T's. And now we are back to the T test. Okay, we're looking at the T statistic. And as long as we have this in our back pocket, right, we're not worried, because we can use Excel's function t.inv to help us find any t. Okay, at least any any critical t, I should say, because of course our computed t, there's always a separate formula for that. For this analysis, there will be n-2 degrees of freedom. So whatever our probability is, right, we're going to have n-2 degrees of freedom. Okay, so when we get into Excel, we're going to see that play out. So step 4, formulate a decision rule. Okay, So we have a hypothesis test where we have equal signs, right? Which means we are dealing with two tails, right? Because we have an equal sign right there in our hypothesis test. And so we are then going to divide our alpha by 2. So if we take that 0.05 divided by 2, right, there is the 0.025. Okay, so that's where that comes from as per usual. And then we want to take that n minus 2. Okay, and that n minus 2 will be the 15. Okay, minus 2 is going to give us 13. And that 15 comes from the fact that there are 15 data points per, I should say 15 observations in our data set. And by 15 observations, what I mean is if this were in Excel as it was before, that's observation 1, observation 2, observation 3, etc. So those 15 observations are going to lead us to an n of 15 minus the 2. Okay, so there is our 13 right here, right? And again, if you plug this into Excel, you will come out with a lengthy number, but if you round it to 3 digits, you'll get 2.16. And the Excel looks like this. 0.025, 13 equals. So when we're done here, if you want to go into Excel and punch that in, you'll come out with 2.160. And of course, it'll actually be the negative one for the reasons we talked about many times before. And you know it's negative and positive because of the symmetry on both sides of the normal curve. Okay? You know what the 0.025 means because that is your rejection region divided by 2. And of course, then this would be the remainder from 0.5, so 0.75. Make it a little more clearly there, but that's 0.75. Okay, so if we establish the rejection region, we then have to ask ourselves, what in the world is our computed t? Because we've just created what's known as our critical t, right? And that critical t is on both sides. So now we want to decide, or we want to find out if our computed t falls either in the rejection region, right, here, or the do not reject region, which is here, okay? And that's where step 5 comes in. Step 5 is fairly intense in terms of the requirements. You see, we're going to get to a bottom line here, but before we get to that bottom line, there's some things going on. The first thing going on is finding the R, okay, finding the R. If we were to calculate the R by hand, right, we would find first that number, the X bar, the Y bar, and then SX and XY, okay? And that's fairly simple because we have Excel at our disposal. Now, the slide is showing us the process without Excel, right? It's just saying do this by hand. And real quick, right, it's saying find your X bar first. Okay, not a problem. Here's my X bar, which is just the average of all of these X's. Great. And then it's saying take your each X minus the X bar. That's right here. Take each X minus the X bar. So 96 minus X bar of 96 gives me a 0. Okay, 96 minus 96, 0. And that 0 is right here. And then the next one, 40 minus 96 gives you a negative 56, okay, which is right here. So if you do that consistently all the way down for all 15 observations, right, you will get data. Well, let me get rid of that. You will get data that looks like this, okay? And as you learned in the earlier chapters in business stats, adding those all up will always give you 0. Multiplying them together gives you a column that looks like this, and then adding them up gives you your numerator for your R. That's all it is right there. and then taking n minus 1, let me see if they've done this too, and then taking your n minus 1, there it is, 15 minus 1 right there, times your standard deviations, which you could find in Excel, or you could do it by hand, but just stdev.s is going to give you the standard deviations of 42.76 for the x's, okay, and the 12.89 for the y's. So that process of getting the r, which is right here, there's some steps involved if you're doing it by hand, but nothing too complicated. But just know your conclusion is 0.865. But let's do it the more efficient way in Excel so that we can get a better understanding of the following steps, which is calculating your t, your computed t ultimately. Okay, so let me pull this and, okay. So I am back to my Excel data, and my Excel data gives me those 15 observations, and here is my calculation, right? It's something called equals Corel. That's the function in Excel that you want to employ in order to get the R. Let me get rid of it and redo it. So you want to type equals C-O-R-R-E-L, open parentheses, and it asks for array 1, which just means insert the data, not the column head, not the words, but the data for the first set of data. So there we go. Hit the comma button and Excel says give me array 2. So click and drag. I've got array 2, close parentheses, hit enter, and there you have it, 0.865 if I am rounding to 3 digits, okay? And that's it, which obviously, there's our R, which obviously is much easier than going through these steps. But as I always say, the steps are there for a reason, because you have to understand what R is before you start using and discussing R. Okay, so it's not enough to just go into Excel and spend 15 seconds doing an equals Corel. If you really understand and want to appreciate what's going on with R, then look at the heading, look at the numerator here, right? It's about the differences, again, like most of our statistics, the differences between the errors and the observations, okay, as our numerator, divided by a standard deviation for both of them. Okay, so we're saying that understand the differences between the errors and each of the observations, and then divide that by the variability of the observations. Okay, now really think about that. Both of those terms are talking about, you know, correlations. It's talking about how certain variables relate to other variables, right, and correcting for the differences. So if you truly want to get into what a variable means, then do it by hand, right? Excel is just there to speed it up. So I always want to underscore the fact that statistics is not about being great at Excel. It's about being great at understanding relationships between variables. And Excel just helps facilitate that, but doing it by hand is valuable to understand those relationships first and foremost. So do it by hand first, and then as you understand it, that's when you start applying the processes and techniques in Excel, okay? All right, so we have an R, which is right here, 0.865. 0.865. Is that a strong R?
Yes.
Yeah, that's a very strong R. The highest it gets is 1, right? So this is 0.865. That's only, you know, 0.14, 0.13 away from 1. Remember, 1 is our highest number that an R can be. Okay, positive 1. And the lowest it can be is negative 1. So if we're talking 0.865, right? This is the halfway point between 0.75 and 1. So we're talking about halfway between here and here. So somewhere around here is 0.865. Very strong, very positive relationship between making phone calls and selling copiers, okay? You have to keep in mind what we're talking about here, making phone calls and selling copiers. So we're seeing that it's very strong. All right, so we've now established the fact that we have a strong relationship, we have a positive relationship, and we are now going to use that data to construct our computed T. So here we go. Here's our formula, right, for the computed T when undergoing a row test or a test of correlation, right? Here's our T. Now, here's the R that we just found. 0.865 is what it is. We know n minus 2. We're taking the square root of that. And then we just take our denominator of 1 minus r squared. 1 minus r squared. So again, you know, when we square stuff, we're trying to get it to be consistent. We take square roots of stuff, we're trying to get it back to our original type of data. This is all standard deviation type of logic. And ultimately, we have a 6.216, also known as our computed T, also known as our test statistic. Okay?
Before you go any further, the one on top, that 0.865, when you're doing that by hand, are you square rooting that 15 minus 2, or are you just multiplying that?
You're square rooting the 15 minus 2.
And also the bottom?
Yes,
okay.
Yes. That's an effort to be consistent. So the 15 minus 2, 13, you're going to put that as a square root before you multiply it times 0.865.
Okay.
So as you're building the model for this, be sure that might be a step you either put in parentheses or just put it in a whole separate cell.
Okay.
Okay. I would just recommend a whole separate cell because, again, it doesn't matter how many steps you have. The bottom line is that your number is accurate. So keep that in mind. All right. So earlier we established the rejection region, right? Our critical T of negative 2.16 and positive 2.16. Here is our computed T, our test stat of 6.216. And look at the language. The test stat 6.216 is greater than the critical T of 2.16. Therefore, we reject the null hypothesis that the correlation is 0. And that is good because we have a positive strong R. Remember that our hypothesis, null hypothesis, was that the R, rho in Greek, is 0. Rho is 0. We don't like that. Never did, because we clearly saw earlier that we have a positive and relatively strong R. So we were hoping from the very beginning that this would be rejected. We were hoping from the very beginning it would be rejected, and turns out it is. This null hypothesis is rejected, and we are not rejecting, okay? We are not rejecting because if you don't reject, then you like something, you prefer something. We are not rejecting the rho being not 0, okay? Because it is 0.865. It is not 0. It is 0.865. Okay, so everything here is consistent. When tested statistically, it turns out that our 0.865 is a good R. It's a statistically sound R. Okay, that was the point of the test. That's what the 6.216 gave us. Let's look at the interpretation here. The data indicate there is significant correlation between the two variables. Okay, we can also observe the correlation is 0.865. Which indicates strong positivity. In other words, as more sales calls are made, more copiers get sold. Please note that that relationship, this analysis, does not provide any evidence of a causal relationship. Again, there's a difference between correlation and causality. Another type of study is needed to test that hypothesis, okay, which we get into a little bit later. So we're done with testing the correlation. Okay, that was this example here, testing the correlation.